Imagine your entire digital life, all your cherished photos, your essential documents, every streaming video you've ever watched. Now take that vast ocean of data, multiply it by billions, and then picture trying to store it all not on pristine, perfect machines, but across thousands upon thousands of inexpensive, off-the-shelf hard drives that are, let's be honest, constantly failing.
Wow.
How on earth do you keep anything safe, accessible, and lightning fast in a world like that? It sounds like an impossible challenge, right? Like a recipe for digital disaster. Well, here on The Deep Dive, our mission is to shortcut your path to being truly well-informed. We take complex topics, a stack of sources, articles, and research, and we try to extract the most important nuggets of knowledge and insight, maybe adding just enough humor and real-world connection to keep you hooked. We want you to feel like you're sitting in on a fascinating conversation, learning what matters most about a topic without getting bogged down in every single detail. Today, we're peeling back the layers on a true titan of technology, something that fundamentally redefined how we manage information at an unprecedented scale. The Google File System, or GFS. This isn't just some dusty piece of tech history. It was a revolutionary idea, a truly groundbreaking system that powered Google's explosive early growth and profoundly shaped the entire future of big data as we know it. We're talking about the very backbone of how massive internet companies manage information, even to this day.
That's absolutely right. When Google was first scaling up, they faced challenges that existing file systems simply couldn't handle. GFS was designed specifically for what they called scalable, distributed, data-intensive applications. And it was a radical departure from conventional wisdom because it proved that high aggregate performance, meaning, incredible speed when you add up all the parts, could be delivered reliably on what were essentially inexpensive commodity hardware. This meant standard, budget-friendly servers, even with the constant predictable failures that come with using so many components. It really redefined traditional file system assumptions, and its influence, as you mentioned, is definitely still felt across the tech landscape today.
Okay, so as we embark on this deep dive, you, our listener, will discover how Google ingeniously turned what most people saw as glaring weaknesses, cheap, unreliable hardware that was bound to break, into one of its greatest strengths. We'll explore how GFS optimized for truly gigantic files, far beyond anything people were used to, and built a system that fundamentally changed how we think about storing and accessing data at an unprecedented scale. We're going to unpack the genius behind its design and why it matters even if you're not building a global search engine yourself. The world GFS was born into, Google's unique needs and challenges. So let's begin by unpacking the context. What made Google's needs so unique that they couldn't just use existing file systems? What were the core realities driving their completely unique design choices? Because like you said, what they built wasn't just an improvement, it was a fundamental reinvention.
It's a crucial question, yeah, because to really wrap your head around GFS, you have to understand the problem it was trying to solve. What's fascinating here is that traditional file systems simply weren't built for the rapidly growing demands of Google's data processing needs at that time. Think about it. They were talking about managing many TBs comprising billions of objects. Billions. We're not talking about a few large databases. We're talking about the raw content of the entire web. Log files from every single search query, intermediate data for complex computations, just vast amounts. If you tried to handle that with conventional file systems, it would be, as the paper says, unwieldy to manage billions of approximately KB-sized files. The sheer scale of the data and the number of individual pieces of data was just too immense for existing solutions to handle efficiently.
Right, so if you try to picture that, traditional file systems were kind of like trying to store an entire ocean in tiny teacups. You'd need an insane number of teacups, and then you'd have to manage all of them individually, constantly spilling, constantly breaking. Sounds like a nightmare. Google needed a completely different kind of container, right? Like a massive, resilient reservoir that could handle data flowing in by the gigabyte, not by the teacup.
Exactly, precisely. And that need, that sheer scale, led to some core observations that profoundly drove the GFS design. These weren't minor tweaks or, theoretical considerations. These observations directly challenged nearly every assumption engineers had previously made about building robust file systems for large organizations. The first, and maybe the most crucial one, was the understanding that component failure is the norm, not the exception. This is a fundamental paradigm shift. GFS was built from hundreds or even thousands of storage machines built from inexpensive commodity parts, cheap parts, lots of them. The problem is, when you combine that many cheap parts, the sheer quantity and quality, or lack thereof, virtually guarantee that some are not functional at any given time. It's not a matter of if something will fail, but when and how often. And we're not just talking hard drives, network cards, power supplies, memory, OS bugs, anything could fail.
That's a really counterintuitive starting point, isn't it? Most system designers try their best to prevent failure. So, let's really try to picture this. Imagine walking into a massive server room, not with gleaming, perfect, expensive machines, but with thousands of budget computers humming away. Picture hard drives that might be a bit flaky, network connections that could glitch out randomly, even human errors or operating system bugs causing problems. You have to assume these things are always happening somewhere all the time. So if your fundamental assumption is that things will break, how does that change your design philosophy?
And that's precisely the point. That reality meant that constant monitoring, error detection, fault tolerance, and automatic recovery must be integral to the system, baked right in. You don't try to prevent every single failure because that's not only impossible at this scale, it's also incredibly expensive. Instead, you design the entire system from the ground up to expect failures and recover automatically without needing a human to jump in every 5 minutes. The system has to be self-healing because manual intervention just wouldn't scale. No way. Okay, the second key observation. Files are enormous. In GFS's world, multi-GB files are common. These aren't just big files. They often contain many application objects, such as web documents, or maybe a vast collection of web crawl data, or the output of some massive batch processing job. Huge.
Right. This is a crucial distinction. We're not talking about your average Word doc or a photo. We're talking about a single file that could contain, I don't know, a significant chunk of the entire internet's raw data, or a massive continuous log of user activity. How did that change the way you think about traditional file systems, which were often optimized for, much smaller files?
It forces a complete rethinking. Yeah. Traditional design parameters like I/O operation and block sizes have to be revisited. Most traditional file systems operate with small blocks, usually a few kilobytes, maybe a megabyte tops. But for files that are multiple gigabytes or even terabytes, using small blocks would be incredibly inefficient. You'd have way too much metadata, too many individual operations, too much overhead. You need to read and write much larger contiguous chunks of data to be efficient. Think bigger blocks. The third critical observation was that data access patterns are fundamentally different. They are append-heavy. What they found was that most files are mutated by appending new data rather than overwriting existing data. Random writes within a file are practically non-existent. Quote, once written, the files are only read and often only sequentially.
Okay, let's visualize that. Think of it like a continuous diary or maybe a massive, ever-growing scroll. You're constantly adding new entries to the very end of the scroll, right? And then when you want to read it, you typically start from the beginning and just scroll through to the end. You're rarely, if ever, going back into the middle of the diary to erase and rewrite something that was already there. That's a very specific pattern, but I guess it makes sense for things like web crawling or blog aggregation.
Precisely. Exactly. This means appending becomes the focus of performance optimization and atomicity guarantees. Atomicity, just quickly, means an operation either completes entirely and successfully or it fails completely, no partial corrupted updates. So, for GFS, ensuring that appends are fast and reliable is where you want your system to really shine. Furthermore, traditional approaches like caching individual data blocks in the client loses its appeal because you're typically streaming through massive amounts of data sequentially, not rereading small bits over and over. So the caching strategies had to change dramatically from what you'd see in a normal file system. Makes sense.
Yeah, that does make sense. Fewer random reads means less need for fine-grained caching.
Right. And finally, the fourth observation, which is actually a strategic advantage Google leveraged, was the ability to co-design applications and the file system API. By relaxing GFS's consistency model in certain ways, making it a bit less strict than traditional file systems, and by introducing powerful specific operations like atomic append, they could vastly simplify the file system without imposing an onerous burden on the applications.
Okay. This is a truly key insight, and it's where a lot of the genius lies, I think. It showed that hyper-specialization, rather than trying to be a generic, one-size-fits-all file system, could unlock immense performance and efficiency. GFS was tightly coupled, almost custom-built, with Google's own applications and their specific needs. This allowed for powerful, very specific features that might seem weird to a general-purpose system, but for Google's unique workload, they were absolutely transformative. It's like designing a highly specialized tool for a highly specialized job.
Exactly. They weren't trying to boil the ocean. They were building the perfect container for their ocean. 2. GFS architecture. Building blocks of a giant.
Okay, so if you've got these unique challenges and these revolutionary observations like expecting failure and dealing with enormous append-only files, how do you actually build this beast? How do you create a system that can handle petabytes of data on unreliable hardware? Let's break down the core components and visualize how they interact. Maybe think of it like a highly specialized, self-healing library for incredibly large books designed from the ground up for efficiency and resilience.
Yeah, that's a good analogy. At its core, a GFS cluster is built upon three fundamental pillars: a single master, multiple chunk servers, and the clients that interact with them. It's a surprisingly simple yet really robust design. First, we have the master. This is the central brain of the entire GFS cluster. And critically, there's only a single master process for an entire cluster, one brain.
Right. Visualize this. This is your librarian, but for a library containing millions of gigantic books. This librarian doesn't actually touch the books themselves. They don't store the content. Instead, they know everything about them. They know where every single piece is located, who has access, how everything is organized. It's the central authority, the ultimate catalog.
Exactly. The master maintains all file system metadata. This includes the entire namespace, which is the file and directory structure, all the folders and file names. It also stores access control information, who can read or write what. Crucially, it manages the mapping from files to chunks, telling you which specific pieces of which book are where. And it knows the current locations of chunks, meaning which specific storage rooms hold copies of each part of each book at this very moment. Beyond that, it handles important system-wide activities such as chunk lease management, which we'll definitely get into, garbage collection of orphan chunks, and chunk migration for balancing data across the system.
So it's the ultimate coordinator, like a very busy, very intelligent librarian with a perfect up-to-the-second catalog basically in their head, and it's constantly communicating with the storage units via these things called heartbeat messages to get their status and give instructions, right? Making sure everything is running smoothly and that it always has the most up-to-date picture of the system.
Exactly. Next, we have the chunk servers. There are multiple chunk servers, typically just commodity Linux machine running a user-level server process. These are the physical storage units, the workhorses of the system.
Okay, so these are the actual storage rooms or shelves in our giant library analogy. Each room holds actual parts of the books, not the whole thing. They are the grunt workers who physically store and retrieve the data.
Right. And files are not stored as single units on these chunk servers. Instead, they are divided into fixed-size chunks. The chosen size is 64 millibit, which, as we mentioned, is much larger than typical file system block sizes. This is a really key design choice we'll dig into more later. Each chunk gets identified by a globally unique 64-bit chunk handle, which is basically a unique ID number for that specific block of data, kind of like a book's ISBN number, but for just a chapter. Chunk servers themselves store chunks on local disks as Linux files. Pretty straightforward there.
Okay, and here's where the crucial reliability part comes in, tying back to that earlier observation about failure being the norm. For reliability, each chunk is replicated on multiple chunk servers. By default, they store 3 replicas. So to visualize this again, every chapter of a book isn't just in one storage room. It has at least 3 identical copies distributed across 3 different physical rooms, maybe even different buildings within a data center. So if one room goes down, catches fire, loses power, whatever, you still have 2 other copies, ensuring your data is safe and continuously available. That's fundamental.
Absolutely fundamental. Finally, we have the clients. This is the GFS client code linked into each application that implements the file system API and communicates with the master and chunk servers.
Okay, so visualize these as the people, or more accurately, the other computer programs that actually want to read or write parts of the books. They're the ones accessing the data, whether it's a search query, a map request, or maybe processing log files.
And here's another critical design choice for performance. Clients interact with the master for metadata operations, like asking where a file is or getting information about its chunks. But all data-bearing communication goes directly to the chunk servers. All the heavy lifting, the actual data transfer, bypasses the master. This is vital because it means the master isn't a bottleneck for the actual transfer of data, it just points the way. Also interestingly, neither the client nor chunk server caches file data in the traditional sense. Because applications typically stream through huge files or have working sets too large to be cached, they usually just read the data as needed. So while metadata is cached heavily, the actual content of the files is typically streamed directly. That's a significant difference from how normal file systems might operate.
Okay, that makes perfect sense. You don't want the librarian handling every single page request, just telling you which room to go to. So how does all this interact in a real-world scenario? Let's walk through a simple read operation. I think this will really help visualize the data flow, especially for listeners new to how distributed file systems move information around. Imagine you're sitting at your desk, needing a specific paragraph from a massive document stored in GFS. Okay, first, you, the GFS client code running in your application, figure out which 64 millibit chunk contains that particular paragraph you need, based on the file name and the byte offset. Second, you send a request to the librarian, the master, asking, where is the chunk for this file at this specific index? You provide the file name and the chunk's position within it. Third, the librarian, the master, quickly looks it up in its memory, its in-memory metadata, and replies, okay, here's the unique ID for that chunk, and you can find copies in storage room A, storage room B, and storage room C. You, the client, remember this information for a little while, caching it locally to make future requests for nearby data even faster. Fourth, you then go directly to one of those storage rooms, let's say the closest one, geographically or network-wise, storage room A, and say, give me the data for this chunk ID, specifically from this byte range. And finally, step 5, the storage room chunk server A reads the data from its local disk and sends it directly back to you. The master isn't involved in this data transfer at all.
Exactly. The key takeaway here is that the master is only involved in that initial lookup, finding the location. Once the client knows where the data is, it goes straight to the source, directly to the chunk servers for all data transfers. This is absolutely vital for performance, ensuring the single master doesn't become a bottleneck as potentially hundreds or thousands of clients simultaneously try to access data. And the client also caches this location information for a limited time, which further minimizes repeated requests to the master for the same chunk, making subsequent reads even faster. It's a brilliant way to offload work from that central brain. 3. The genius of design choices. Optimizing for Google's world.
That's a really clear picture of the architecture. Now let's dig into some of the specific, maybe even counterintuitive choices GFS made that, for their specific problems, turned out to be absolutely brilliant. These decisions really highlight how understanding your unique workload can lead to revolutionary design. Let's start with what might seem like a wildly inefficient choice in a traditional file system, the massive 64 millibit chunk size. As we mentioned, this is a key design parameter much larger than typical file system block sizes, which are usually in the kilobytes, maybe low megabytes, so why not smaller chunks? What were the big upsides to this, and what were the surprising downsides they had to engineer around?
Well, the advantages of a large chunk size are pretty significant, especially for Google's workloads, which, remember, involve very large files and sequential access patterns. First, it dramatically reduces client interaction with the master. For large sequential files, the common case, a client only needs to ask the master for a chunk's location once for every 64 MB block. This reduces clients' need to interact with the master, greatly lessening the load on that single central master. If chunks were smaller, say 1 MB, the master would be absolutely flooded with location requests. Second, it provides significant network efficiency. With such large chunks, clients are much more likely to perform many operations on a given chunk once they've located it. This allows them to keep a persistent TCP connection open to the chunk server over an extended period, reducing the overhead of constantly setting up and tearing down network connections. Think of it like keeping a long-distance phone call open rather than hanging up and redialing every few seconds. Much more efficient. Third, and this ties back to the master's capability, it results in smaller metadata. Fewer, larger chunks means substantially less metadata for the master to manage overall, less stuff to keep track of. This is critical because it enables the master to keep all its metadata in memory, all of it. This in-memory storage, as we'll discuss more, is key to the master's speed and efficiency. For example, a single 64 MB chunk only requires about 64 bytes of metadata in the master's memory, incredibly compact.
Okay, those are compelling advantages. But, like you said, there are always trade-offs. What were the disadvantages of such a large chunk size, and how did they mitigate them?
Right. The main disadvantage, even with clever tricks like lazy space allocation, is the potential for hotspots for small files. If many clients need to access a small file, say an executable program or a configuration file, and that file fits entirely within a single 64 MB chunk, well then, the few chunk servers storing that chunk may become hotspots. Everyone is trying to get that one tiny chunk from the same limited set of rooms, causing a traffic jam.
And Google actually ran into this, right? I remember reading a real-world example they encountered was when an executable was written to GFS as a single chunk file and then started on hundreds of machines at the same time. You can just picture it. Hundreds of machines all rushing to get the same single chapter from one specific storage room, causing a massive bottleneck. That's a classic hotspot in action.
Exactly. And the solution wasn't to change the chunk size for all files. That would lose the other benefits. Instead, they adapted. They addressed this by storing such executables with a higher replication factor, maybe 5 or 10 copies instead of 3, spreading the load across more rooms, and by having the batch queue system stagger application start times. So basically spreading out the demand over time. Even if it's the same chapter, they don't all rush to the same place at the exact same moment. This highlights that you can often design around the downsides if you truly understand your workload and have control over the applications using the system.
That makes a lot of sense. Smart workarounds. Now let's talk about metadata. Keeping the brain agile and resilient. The master holds all the critical knowledge, but how is that information managed to be both incredibly fast and absolutely safe from failure? Because if the master goes down and loses its metadata, the whole system basically collapses, right?
Absolutely. It's the Achilles heel if not done right. The master stores three key types of metadata: the file and chunk namespaces, which is the directory structure, the mapping from files to chunks, connecting files to their 64 metal B data blocks, and the locations of each chunk's replicas, meaning which chunk servers currently hold copies of which chunk. The first genius choice here is in-memory speed. All metadata is kept in the master's memory. All of it. This is why master operations are fast. Accessing data in RAM is orders of magnitude faster than hitting a disk. It also allows the master to periodically scan through its entire state in the background for critical housekeeping tasks like garbage collection or re-replication, ensuring the system is always self-healing and optimized. This periodic full scan would be impossibly slow if the metadata were primarily disk-based. However, memory is volatile, right? If the master crashes, data in memory is poof, gone. So for persistent logging for safety, the critical parts, the file and chunk namespaces and file-to-chunk mapping, are also made persistent. They do this by logging mutations to an operation log stored on the master's local disk and replicated on remote machines.
Okay, let's visualize this log. Think of it as the librarian's indispensable, meticulously kept journal. Every critical change, a new file created, a chunk added, a file deleted, a directory renamed is written down here in exact order, and then immediately copied to other safe remote locations, like backup journals. This journal is the single persistent source of truth for the system's state. If the library burns down, you can rebuild the catalog from the journals.
Precisely. This log is central to GFS, as it's the only persistent record of metadata and serves as a logical timeline that defines the order of concurrent operations. Absolutely critical for consistency. Client operations are not made visible to clients until metadata changes are made persistent, meaning until they are flushed to disk locally and remotely on the replicas. This ensures that even if the master crashes catastrophically, it can always reconstruct its exact state by replaying the log from the last known good point, bringing the entire system back to a consistent state. Now, here's a seemingly odd but actually very clever choice: chunk locations, the live map. The master does not store chunk location information persistently. It doesn't write down where the chunks are permanently. Instead, it asks each chunk server about its chunks at master startup and whenever a chunk server joins the cluster. It polls them.
Huh. That sounds counterintuitive again. Why wouldn't you want a permanent record of where every chunk is? Wouldn't that be safer and faster? Relying on memory seems risky.
It actually turns out to be much simpler this way, and it elegantly eliminates the massive headache of keeping the master and chunk servers in sync as chunk servers join and leave the cluster, change names, fail, restart. In a system with hundreds of servers and components failing constantly, these movements happen all too often, all the time. Trying to constantly synchronize a permanent, authoritative map of chunk locations with the ever-changing reality on thousands of chunk servers would be an absolute nightmare of complexity and potential inconsistencies. By just polling the chunk servers, asking them, hey, what chunks do you have right now? The master always gets the most accurate, live information directly from the source. As the paper says, the chunk server itself has the final word over what chunks it does or does not have. By trusting them, the system remains robust and surprisingly simple. It's a beautiful example of smart distributed systems design. And to make sure recovery is quick, they use checkpoints for fast recovery. The master checkpoints its state whenever the log grows beyond a certain size. This means it periodically takes a snapshot of its entire in-memory state and writes that snapshot to disk and replicates it. When recovering from a crash, it first loads the latest checkpoint, this compact B-tree-like form, directly into memory. Then, it only needs to replay the relatively small number of log records that occurred after that checkpoint was taken.
Got it. So visualizing that again. Instead of our librarian having to reread their entire journal from day one every time they restart after a nap, they periodically take a snapshot of their current mental state, their entire catalog, as it stands. Then, they only need to catch up on the few entries that have been added to the journal since the last snapshot. This drastically speeds up recovery time and improves availability, which is absolutely crucial when you have a single point of coordination like the master. Faster restarts are better. Okay, now here's where GFS really seems to depart from traditional thinking. And it's a crucial differentiator that enables much of its scale and resilience. It has a relaxed consistency model. For listeners new to distributed systems, what does that actually mean for our data, the information that's being stored and accessed? Does it mean it's just like eventually consistent, or is there a stronger guarantee? What are we trading off here?
That's a great question, and it's a core concept, maybe one of the trickiest in distributed systems. GFS is designed to support our highly distributed applications well, but remains relatively simple and efficient to implement. It makes a conscious trade-off, yes, but a very intentional and, frankly, useful one, especially given the reality of constant component failures and the specific needs of Google's apps. Let's break down the guarantees. First, file namespace mutations. Things like creating a file, renaming a directory, deleting a file are atomic. They are handled exclusively by the master, and the master's operation log guarantees a global total order for these operations. So you won't end up with two files having the exact same name simultaneously, or conflicts during renames. That level of consistency is important, and it's guaranteed. The real nuance comes with data mutation states, which describe what happens when you actually write data into a chunk. The paper introduces a helpful classification here. When a mutation, like a simple write, succeeds without interference from concurrent writers, the affected region is defined, and by implication consistent. This means all clients will always see what the mutation is written. It's clear, it's perfect, it's what you'd normally expect, consistent and defined. However, if there are concurrent successful mutations, meaning multiple writers trying to write to the same part of a file at the same time, this leaves the region undefined but consistent. This means all clients see the same data, but it may not reflect what any one mutation has written. It might be a mix, mingled fragments from multiple mutations. Imagine a shared whiteboard where multiple people are writing simultaneously in the exact same spot. Everyone sees the same final, messy result, but maybe no single person's complete input is fully legible. The system ensures everyone sees the same mess, so it's consistent across all viewers, but it's undefined because no single write fully won that space. And then, if a mutation failed partway through, maybe due to a network error or a chunk server crash, it makes the region inconsistent, hence also undefined. This is the worst case scenario where different clients may see different data at different times. However, the system is designed to detect this, like with checksums, which we'll get to, and for applications to recover from it, usually by relying on checkpoints or retrying. But the real special magic, as you called it, comes with a GFS extension called atomic record append. This is a specific type of mutation where the client specifies only the data it wants to write, and GFS itself figures out where to put it. GFS appends it to the file at least once atomically, at an offset of GFS's choosing, which it then returns to the client.
Okay, let's visualize this, because it sounds like a critical differentiator for how Google used GFS. Imagine multiple people simultaneously writing notes into the same shared ledger. Instead of trying to claim a specific line number in the ledger, which could lead to a messy race condition, especially in a distributed system with network delays, they just say, add this note, and the system makes sure each note gets added completely, one after another somewhere near the end. Even if their exact order isn't strictly predictable across all copies immediately, each note is whole. The system handles the where to put it part and ensures the entire record is written without overlapping or corrupting other records.
Exactly, that's the core idea. This is useful for implementing multi-way merge results and producer-consumer queues that many clients can simultaneously append to without additional locking. A very common pattern in Google's data processing pipelines. Now, because GFS guarantees at least once delivery for these appenders to handle potential retries after failures, duplicates or padding might appear. But these occupy regions considered to be inconsistent and are handled by the application, not the file system itself. The application knows to filter them out later, maybe using unique IDs within the records. There's also a small detail called the stale data window. If you're reading a file and a chunk server you happen to connect to had been down and missed some updates from the master about chunk versions, you might temporarily read a stale replica. But for append-only files, which again are very common, this usually just means you get a premature end of chunk. You just don't see the very latest data yet, rather than completely outdated, incorrect data from the middle of the file. When you retry the read, the client will likely get updated locations from the master and see the correct data. Plus, the master actively removes stale replicas during its regular garbage collection, so this is a very short-lived potential issue.
Okay, so given these nuanced consistency guarantees, what are the implications for applications? How do Google's applications actually work with this relaxed consistency model? given that a traditional developer might freak out and demand strict, immediate consistency everywhere.
Yeah, that's where the co-design aspect really pays off. Google applications are specifically designed to accommodate the relaxed consistency model with a few simple techniques already needed for other purposes. It's about building a robust application layer on top of a powerful but slightly more flexible file system, rather than demanding the file system handle every single edge case of perfect consistency, which would make it slower and more complex. One key technique is simply relying on appends. As we've said, practically all our applications mutate files by appending rather than overwriting. This mode of operation is inherently far more efficient and more resilient to application failures than random writes. If an append fails, you just retry it, and GFS handles the at least once delivery. This design choice permeates everything they do with large data. Another really important technique is checkpointing. Writers periodically checkpoint how much has been successfully written. This means they log their progress in a separate, consistent way, maybe writing a marker to a separate file or location. Readers then only verify and process only the file region up to the last checkpoint, which is known to be in the defined state. So, if an application crashes mid-process, it can restart from the last known good checkpoint, safely ignoring any potentially undefined or inconsistent data that might appear after that point in the main data file. And for those concurrent appends, they use self-validating, self-identifying records. It's quite clever. Each record prepared by the writer contains extra information like checksums so that its validity can be verified. So it's not just raw data being appended. Readers can then identify and discard extra padding and record fragments using the checksums. And if duplicates are a potential problem because of the at least once appends, they embed unique identifiers in the records, which the reading application can then use to filter out any duplicate deliveries.
Ah, okay. So visualizing that, again, each entry in that shared ledger isn't just raw text. It has a little tag saying, I'm complete and valid, maybe using a checksum, and a unique serial number, like a timestamp, plus a unique ID. So if you're reading the ledger, you can easily filter out anything that looks incomplete or like a duplicate without the file system itself having to guarantee perfect byte-for-byte identical replicas across all copies at all times. That flexibility seems like a major design win for achieving scale and resilience in a distributed environment where perfect consistency is just prohibitively expensive and complex.
It absolutely is. It pushes some complexity to the application, but only complexity the application likely needed to handle anyway for general robustness. 4. Under the hood. How data moves and stays safe.
That's a really profound shift in thinking about data consistency. Okay, now let's get even more granular. We understand the components and the big picture ideas, but how does the data actually move through this distributed system, especially during writes? And how do they ensure everything stays robust, even with constant failures? It sounds like a complex dance.
It is indeed a dance, yeah, a carefully choreographed one. A mutation, remember, is any operation that changes a chunk's contents, or metadata, and crucially, each mutation is performed at all the chunk's replicas. So if you write to a chunk, that write has to make it successfully to all 3, or however many copies. This brings us to leases and the write dance. To make sure writes happen in the same order everywhere, we use leases to maintain a consistent mutation order across replicas. The master grants a chunk lease to one of the replicas, which we call the primary. This primary replica is temporarily in charge of ordering writes for that specific chunk. This primary picks a serial order for all mutations to the chunk. All the other replicas, the secondaries, then follow this order. The lease has a timeout, usually around 60 seconds, so if the primary fails or becomes unresponsive, the master can grant a new lease to another replica after a short delay, ensuring writes can continue.
Okay, let's visualize this. Think of the primary chunk server as having temporary, exclusive writing rights for a specific chunk, like holding a talking stick for that chunk. It's like the designated scribe for that particular chapter. Everyone else who wants to write to that chapter has to go through this primary scribe. The scribe then ensures all copies get the changes in an organized, consistent sequence, even if multiple people are trying to write at once. It imposes order on potential chaos.
Exactly. Now, let's walk through the write control and data flows step by step. Figure 2 in the original paper illustrates this really well, and it helps visualize the separation. Step 1. You, the client application, want to write some data to a chunk. You first ask the master, who's the current primary for this chunk, and where are the other copies, the secondary replicas? Fuck 2. Step 2. The master replies with the identity of the primary chunk server and the locations of all the secondary chunk servers. You, the client, cache this information for a short time for future mutations to the same chunk. Step 3. Now, This is crucial. You now push the data to all the replicas, meaning to the primary and all the secondaries. You can do this in any order, often simultaneously, based on network topology. Each chunk server temporarily stores this incoming data in an internal LRU buffer cache. LRU just means least recently used. It's a standard caching strategy. So picture this. You've just sent your raw data simultaneously to all 3 storage rooms. They're holding it, waiting for the official instructions on where and when to permanently commit it. This step effectively decouples the data flow from the control flow for better performance. Step 4. Once all replicas confirm they've received the data into their temporary buffers, you send the actual write request, the control message, only to the primary chunk server. The primary, because it holds the lease, assigns consecutive serial numbers to all the mutations it receives, ensuring order even if requests arrive from multiple concurrent clients. It then applies the mutation to its own local copy from its buffer using the assigned serial number. Step 5. The primary then forwards the write request, including the serial number it assigned, to all secondary replicas. It tells them, okay, apply serial number 5 now from your buffer. Step 6. The secondaries receive this control message, apply the mutation from their buffer in the exact same serial order as the primary, and reply back to the primary, confirming they've completed it. Step 7. Finally, the primary collects confirmations from all secondaries and replies back to you, the client, confirming that the write was successful across all replicas. If there are any errors reported by any replica during this process, the primary tells the client the request failed. The client then simply retries the whole process, likely starting from step 1 again, perhaps after a short back off. This ensures atomicity and eventual consistency for that specific write operation.
That is incredibly elegant. I see the decoupling now. The heavy stuff gets moved as fast as possible, often simultaneously to all the chunk servers using the best network paths, and they just stage it temporarily. And then the control messages, the commit instructions, and the crucial ordering information follow, ensuring that all replicas apply the same changes in the same sequence. And if there's an error at any point, you, the client, just retry the whole thing, making it resilient to partial failures. It's designed to always get to a good state eventually. Very clever.
Yes, and this approach also leads to efficient data flow during that initial data push in step 3. The data is pushed linearly along a carefully picked chain of chunk servers in a pipelined fashion. End quote. So the client sends the data maybe to the closest chunk server. Let's call it S1. S1 immediately starts forwarding that data to the next closest chunk server in the chain, S2, even before it has received the entire chunk itself. S2 forwards it to S3, and so on, like a pipeline.
Okay. Picture this. It's like a bucket brigade or a relay race for data. Each machine in the chain starts passing the data along as soon as it starts receiving it. It uses its full outbound network bandwidth to send to the next closest machine in the chain, maximizing efficiency and minimizing latency. This approach avoids bottlenecks and high latency links by optimizing for the network topology, ensuring the data moves as fast as possible across the distributed system without machines waiting unnecessarily. Smart pipelining. Okay, brilliant. Now let's talk about something else that sounds almost like magic. The magic of snapshots. GFS can create a copy of a file, or even an entire directory tree, almost instantaneously and at low cost. This sounds impossible for multi-terabyte datasets. You're definitely not copying terabytes of data around in milliseconds, so how is this possible? What's the trick?
You're right, we're definitely not copying terabytes instantly. The trick is a standard but incredibly clever technique called copy-on-write. It's a powerful concept used in many areas of computing for managing large datasets efficiently. Here's the process in GFS. When a snapshot request comes in for a file or directory, the master first revokes any outstanding leases on the chunks of the files being snapshotted. This is crucial because it pauses any writing to them, giving the master full control for a moment. 2. Then the master simply duplicates the metadata for the source file or directory tree in its own memory and logs this metadata change persistently. 3. Crucially, the newly created snapshot files point to the same chunks as the source files. So picture this. You get a new library card for the snapshot, but it points to the exact same physical books, chunks, as the original library card. No actual data is copied at this point. It's all just manipulating pointers in the metadata. It's essentially just creating a new name that points to the existing data block super fast. 4. Now here's the copy on write part. The first time a client wants to write to a chunk that is part of both the original file and the snapshot file, the master knows this because the chunk's reference count is greater than 1. The master intervenes just before granting the write lease. 4. Now here's the copy on write part. 5. It notices the chunk is shared. So the master picks a new chunk handle, a new unique ID for a new chunk. It then asks each chunk server that has a current replica of the original chunk to create a new chunk with this new ID. This new chunk is created physically on the same chunk servers that hold the original replica. The chunk servers perform a local copy of the data from the old chunk to the new chunk.
Ah. So only that specific chapter, that 64 MenyOB chunk that's about to be modified, is copied to a new set of storage rooms, new chunk files, but on the same physical machines. The data travels locally on the disk, not over the network. That's incredibly fast.
Exactly. It's a local disk copy, which is much faster than a network copy. Then the master updates the metadata for the file being written to point to this new chunk, grants the lease to the primary for the new chunk, and the client performs the write, completely unaware that this copy just happened behind the scenes.
That is incredibly efficient. You only copy the data blocks that actually change, not the entire file or directory tree, saving vast amounts of time, disk space, and network bandwidth. Brilliant use of copy on write V, keeping it alive. Fault tolerance and performance in practice. That copy on write mechanism is really elegant. It shows how GFS leverages existing hardware in smart ways. But GFS is also built for extreme robustness, right? How does it keep running smoothly and ensure data integrity day in, day out, especially when things do inevitably go wrong in a system with thousands of components? This feels like where the rubber meets the road for reliability.
Yeah, a lot of that ongoing magic happens through continuous master operations, working tirelessly behind the scenes to keep the system healthy. First, there's namespace management and locking. Multiple master operations, like creating files or snapshotting directories, can run concurrently to improve throughput. To ensure correctness and prevent nasty conflicts, GFS uses locks over regions of the namespace, basically, locks on file and directory paths. Operations acquire specific read or write locks before running. For example, a write lock on dir prevents anyone else from creating or deleting files directly within dir while the lock is held, but reads can still happen.
Okay, so picture this. Even though it's one librarian handling all requests, they can manage multiple patrons at once by having a clear system of locking specific shelves or sections of the catalog temporarily. So two people can create new files in the same directory concurrently, dirfoo and dirbar, as long as they acquire read locks on dir and write locks on the individual file names. The locks ensure orderly access and prevent race conditions that could corrupt the namespace. Smart locking.
Then there's the crucial replica placement strategy. A GFS cluster isn't just distributed across machines, it's highly distributed at more levels than one, with chunk servers strategically spread across many machine racks. The placement policy aims to maximize data reliability and availability, and also maximize network bandwidth utilization. It's not random.
So it's not enough to just put copies on different machines. You must spread chunk replicas across racks. Why is that so important? Picture this. Your 3 copies of a chunk aren't just in different rooms in the same building, but maybe in different buildings entirely, represented by different racks in the data center.
Exactly. This ensures that some replicas of a chunk will survive and remain available even if an entire rack is damaged or offline, for instance, due to a power outage affecting an entire rack, or maybe a network switch failure for that rack. It provides fault tolerance beyond just a single machine failure. It also means traffic, especially reads, for a chunk can exploit the aggregate bandwidth of multiple racks, potentially improving performance by not bottlenecking on the network connectivity of just one rack. And GFS is constantly engaged in continuous maintenance, specifically the creation, re-replication, and rebalancing of chunk replicas. Things are always changing. Chunk replicas get created for 3 main reasons. 1, initial creation when a file is first written. 2, re-replication if a copy is lost due to a chunk server failure, bringing it back up to 3 replicas. And 3, rebalancing to spread data and load evenly across the cluster over time. When creating new chunks, the master intelligently tries to place them on chunk servers with below-average disk space utilization. Makes sense. It also limits the recent creations on any one server to prevent a newly added server from being immediately swamped with write traffic and becoming a hotspot. It tries to spread the load proactively.
And what happens if a chunk server actually fails and data becomes under-replicated? Say, you only have 2 copies left instead of 3. Does someone get paged?
No, hopefully not. GFS doesn't wait for human intervention. The master detects this condition quickly via the missing heartbeat messages and the lack of the chunk server in its polling. It then re-replicates a chunk as soon as the number of available replicas falls below a user-specified goal, like 3. It prioritizes chunks based on how many replicas are missing. A chunk with only 1 replica is higher priority than one with 2, or if the lack of replicas is blocking client progress. This is the self-healing aspect in action, constantly working to ensure data safety. For the actual re-replication, the master instructs a healthy chunk server to copy the chunk data directly from an existing valid replica. This is done efficiently, often leveraging network topology, maybe copying from a replica on the same rack if possible. The master also limits the numbers of active clone operations, cluster-wide and per chunk server at any given time. This prevents internal maintenance traffic from overwhelming the network and impacting client operations. It throttles itself.
Right. To keep things running optimally over the long term, the master also rebalances replicas periodically. What does that involve?
It basically shuffles chunks around to equalize disk space usage and load across all chunk servers, maybe moving some chunks from a nearly full server to a less full one. It also helps gradually fill up a new chunk server when one is added to the cluster, rather than instantly swamping it with new data and the heavy write traffic that comes with initial placement. It's a constant background optimization process, like a diligent groundskeeper always tending to the garden, keeping everything balanced. Another critical aspect for managing storage is garbage collection, which GFS handles through a clever mechanism called lazy deletion. When a file is deleted by an application, GFS does not immediately reclaim the available physical storage. The file isn't gone instantly. Instead, it's simply renamed to a hidden name that includes the deletion timestamp. It's still there, just hidden. This hidden file is then only truly removed, and its chunks marked for deletion after more than 3 days by default.
Oh, okay. So visualizing that. Your deleted files don't instantly vanish. They go into a special time-delayed recycle bin that only gets emptied every few days. This provides a crucial safety net against accidental, irreversible deletion, which must be incredibly valuable in a fast-moving production environment where mistakes can easily happen. It's a simple yet highly effective form of accidental data recovery.
Exactly. Then, during its regular background scans, the master identifies orphan chunks, chunks that are no longer linked to any file, neither active nor recently deleted hidden files. It then tells the chunk servers holding those orphan chunks to actually delete their copies, freeing up the physical disk space. This approach is simple and reliable in a large-scale distributed system where component failures are common because it avoids complex, high-overhead distributed transaction coordination for immediate deletion. It's simpler to just clean up later. And one last piece of master magic: stale replica detection. How does it know if a replica has missed updates? Each chunk has a chunk version number. Every time the master grants a new lease for a chunk, usually because a write is about to happen, it increases this version number and informs all the current replicas of the new number. If a chunk server was down or disconnected and missed these lease grants and subsequent writes, its copy will have an older, stale version number.
Got it. So the master knows the current version number for every chunk. And when a client asks for chunk locations, the master simply doesn't include any replicas that report an old, stale version number.
That's right. The master effectively removes stale replicas in its regular garbage collection and simply considers a stale replica not to exist at all when it replies to client requests.
So you're always pointed to the most up-to-date, consistent data. It's like the librarian knowing which copies of a book are the current edition and which ones are outdated due to missing pages, and making sure you only get pointed to the latest edition. This is key to maintaining consistency despite failures. Okay, this is all incredibly robust. But with so many disks and potential failures across thousands of machines, how does GFS prevent silent data corruption? It's not enough to just compare replicas, right? Because, as we discussed, they might legitimately diverge slightly due to that relaxed consistency model and atomic appends. You need a way to verify the data on each replica independently.
Absolutely crucial point. This is where ensuring data integrity with checksums comes in. You cannot trust the hardware implicitly. Each chunk server uses checksumming to detect corruption of stored data. A 64 MB chunk is broken down internally into smaller 64 KB blocks, and each of these small blocks has its own 32-bit checksum stored alongside it.
Okay, picture this. Every little 64 KB piece of your data has its own unique verifiable fingerprint stored right next to it. If even a single bit flips incorrectly due to a disk error, a network glitch during transfer, or even, a cosmic ray hitting the server, it happens. That fingerprint will no longer match the data, and you'll know the data is corrupted instantly. It's like a silent guardian for every block of your information.
Precisely. And for reads, the chunk server verifies the checksum of data blocks that overlap the read range before returning any data to the requester, either a client or another chunk server. If a block fails its checksum verification, the chunk server returns an error to the requester. The requester then knows that replica is bad, will read from other replicas, and the master will be notified to clone the chunk from another replica to repair the corrupted one. This mechanism ensures that clients should never receive corrupt data, even if disk silently fails or data gets garbled somewhere. The paper also notes this has little effect on read performance because the checksum verification is computationally cheap and can often be overlapped with the disk I/O operations, meaning it doesn't usually add significant latency. They also proactively scan inactive chunks during idle periods, scrubbing the data to catch corruption and rarely access data before it's actually needed. This prevents nasty surprises later on.
Okay, so after all this complexity and this intense focus on fault tolerance and data integrity, what about real-world performance and workload patterns? Does all this overhead make it slow, or is it actually fast in practice?
No, it was definitely fast enough for Google's needs and quite impressive given the hardware. GFS demonstrated solid performance in real-world clusters. For example, one cluster mentioned sustained a 580 millibeats aggregate read rate for a week, and individual clients could often achieve hundreds of MBs in read rates, especially for sequential reads.
That's incredibly fast, especially considering it's built on commodity hardware that's expected to fail. So despite all the resilience layers and the distributed nature, it's still highly performant, which really speaks volumes about the design choices, like the large chunk size and direct client chunk server communication.
Exactly. And the master, despite being logically centralized, can easily keep up with the metadata load. It could handle 200 to 500 operations per second sustained, which translates to many thousands of file accesses per second because most accesses are data only to the chunk servers. The master is not a bottleneck in practice for their workloads, thanks to its in-memory design and the offloading of data traffic. This really dispelled the conventional wisdom at the time that a single master in a large distributed system would inherently be a performance bottleneck.
What about recovery time? We talked about re-replication, but how long does it actually take to fix things when they break, like when a chunk server fails and data becomes under-replicated? Because fast recovery is just as important as fault tolerance itself.
Right, recovery needs to be quick to maintain the desired level of redundancy. GFS was designed for fast recovery. In one experiment cited in the paper where a single chunk server failed, holding about 600 gigabytes of data across roughly 10,000 chunks, all those chunks were restored back to 3 replicas in just 23.2 minutes. That's an effective replication rate of about 440 millibs restoring the data across the cluster. Even more impressively, with a simulated double failure, 2 chunk servers dying simultaneously, making some chunks critically under-replicated with only 1 copy left, those critical chunks were restored back to at least 2 replicas within just 2 minutes.
Wow, that's phenomenal speed. That highlights the system's incredible resilience in practice. Quick recovery means even if multiple components fail, the system rapidly heals itself to prevent data loss and restore the desired safety margin. And the workload breakdown they measured also consistently showed that large reads, often sequential, and large sequential writes that append data dominated the actual usage patterns, completely validating their core design assumptions about focusing on append-heavy, large file workloads. This wasn't just a theoretical exercise, it demonstrably worked incredibly well for Google's real-world needs. 6. Lessons learned in the enduring legacy of GFS. GFS was absolutely groundbreaking, no doubt, a true pioneer in large-scale distributed systems. But the journey of building, deploying something of this magnitude, especially back then, wasn't without its bumps or surprising discoveries, I imagine. What did Google learn from actually building and running GFS in the real world? Were there unexpected challenges?
Oh, definitely. One of the biggest insights from their operational experience was dealing with the operational realities of working at this scale with commodity components. They found that some of our biggest problems were disk and Linux related. Not necessarily GFS logic itself, but the underlying layers. For instance, issues where the disk and the kernel to disagree about the drive's state could lead to silent data corruption, which was a major motivation for implementing the robust checksumming we just discussed. They learned not to trust the hardware or even the OS perfectly. They also faced unexpected Linux kernel limitations regarding file system operations like think, for ensuring data durability, and memory mapping files, which sometimes had performance issues or tricky semantics at scale. These required workarounds and, in some cases, even kernel modifications to achieve the desired performance and reliability.
That really underscores that even with a brilliant, high-level distributed system design, the nitty-gritty details of interacting with the physical hardware and the underlying operating system can present significant unexpected challenges. It's a reminder that theory meets messy reality. But Google's ability, as a large company controlling its environment, to actually improve the kernel and share the changes with the open source community highlights a unique advantage they had in being able to push the boundaries of what was possible across their entire software stack.
Absolutely. Despite these operational challenges, GFS's influence and legacy are undeniable and truly far-reaching. GFS fundamentally departed from traditional file system assumptions and proved that a radically different approach could not only work but excel for internet-scale data. It deliberately focused on commodity hardware, extreme fault tolerance baked in from the start, and optimizing for append-heavy workloads, which were previously considered somewhat niche but turned out to be the dominant patterns for big data processing.
Yeah, this paper, published back in 2003, became a foundational text in distributed systems, a real benchmark that people studied and learned from. It directly inspired countless other major systems, most notably the Hadoop Distributed File System, HDFS, which became the backbone of the open-source big data ecosystem and is still widely used today in various industries, from finance to scientific research. It showed the world that a centralized master could scale effectively if designed correctly, like keeping metadata in memory. And it demonstrated that simplifying consistency models for specific application needs was a powerful and often necessary design choice for distributed systems aiming for massive scale and resilience. It really shifted the way engineers thought about building large-scale storage infrastructure.
So why this matters to you, the listener, even if you're not planning to build your own distributed file system tomorrow. The GFS paper is more than just a technical document. It's really a masterclass in systems thinking. It shows how to build a robust, scalable system by explicitly embracing the reality of failure, by deeply understanding and optimizing for unique workload patterns, and by making intelligent, deliberate trade-offs. It champions simplicity where possible, even within immense complexity.
Yeah, it fundamentally demonstrates that when you're dealing with truly massive amounts of data, you often can't just scale up by buying bigger, more expensive, supposedly more reliable machines. You have to scale out using many smaller, less reliable components, but designing the system intelligently to handle that reality. This deep dive, hopefully, reveals some of the hidden infrastructure behind much of our modern digital world. Every time you stream a video, search the web, use a cloud service, or interact with a large online platform, you are indirectly benefiting from the core principles and architectural patterns pioneered by systems like GFS. These aren't just abstract academic ideas. They're the practical bedrock of the internet as we experience it today. Outro. So we've taken a pretty deep dive into the Google file system today. It was a pioneering system that really defied conventional wisdom and redefined what was possible with large-scale data. It's a fascinating story of designing for resilience in the face of constant expected failures, optimizing for massive scale by thinking in these huge chunks, and creating a highly specialized system that became the essential backbone of Google's early explosive growth.
Absolutely. It fundamentally reshaped how we approach large-scale data storage. It demonstrated that you could achieve incredible efficiency, fault tolerance, and high performance, even with inexpensive commodity components, but only by truly understanding the application workload and the messy nature of failure in large systems. It's really a testament to thinking differently about seemingly impossible problems.
So as you interact with the vast digital world today, maybe take a moment to think about the immense, largely invisible infrastructure working tirelessly behind the scenes to make it all seem so seamless. And perhaps consider how these core principles we discussed, embracing failure as a design input, scaling through distribution, focusing on the true usage patterns, making smart trade-offs, how they might be applied to challenges in your own life or work, no matter the scale. It's a powerful framework for problem solving beyond just file systems. Thank you so much for joining us on this deep dive.